Well, good afternoon from Ithaca, New York, home of Cornell University. My name is Nicholas Phillips, and we are so glad that you're joining us. Today is all about combining engineering designs and the science of simulation. For those non-engineers or even those just starting their careers, needing to learn the big ideas are very much accessible, even if math really isn't your thing. The democratization of simulation will enable design engineers and other non-specialists to unleash the power of simulations earlier in the design cycle, leading to better products. And with that, joining me and welcoming Rajesh Bhaskaran, the Swanson Director of Engineering Simulation for Cornell Engineering. He is also faculty author of finite element analysis and fluid dynamic simulation using ANSYS certificate programs. And those links can be found right there in the chat. And just a couple of quick housekeeping things before we get started. Just to remind our audience, we will be taking your questions, so please feel free to put those in the chat there. And also, we will, again, be sharing some helpful resources in the chat, so keep a lookout for those as well. And with that, Rajesh, thank you so much for joining us in studio
pleasure.
Today. We really appreciate it. So I really want to kind of start off our conversation with something you mentioned before we were even talking about having this keynote. And something you mentioned was, how is it that engineers and some engineering students understand a project conceptually, like, building a bridge or a wind turbine, but not understanding how it'll work in the real world or in real simulations?
Thank you, Nick, for that question. Essentially, simulation is using computers and software to solve mathematical models that we have known for a long time. Mm-hmm. And it's only in the last few decades that we have had the technology to solve these mathematical models approximately. So you might understand, maybe you have a CAD design mm-hmm. of your bridge or of your parts of a car. Mm-hmm. And if you want to know how it's going to behave, say if it's going to break or what kind of factor of safety you have, mm-hmm. you have to understand the science in terms of how that mathematical model is built, and mm-hmm. then how do you solve that using these tools mm-hmm. that we have. But as you mentioned, you need to understand the science at a conceptual level mm-hmm. and not get into the nitty-gritty, because we have these amazing tools, and ANSYS is the one we use in our teaching, but you could use any similar tool that'll do the detailed mathematical nitty-gritty for you. And mm-hmm. I find that very liberating, because mm-hmm. I think understanding the science is exciting, but you see, I can apply the science mm-hmm. and solve all these exciting problems. And so you can go quickly from understanding the science mm-hmm. to solving, exciting applications, some of which I'll show mm-hmm. that I have in the certificate programs mm-hmm. from ANSYS.
Mm-hmm. And how can we bridge that gap between, utilizing the science to help us influence the outcomes of what we're looking for? So, for example, how much force can a wind turbine blade handle, for example, or a pressure vessel?
Yes, yeah. Thank you for that question, Nick. So that's actually one of the main things that engineers use simulations for mm-hmm. is I'll show you some examples later on. Mm-hmm. Let's say you have a CAD model of your wind turbine blade, which I will show later. And mm-hmm. then you put it into the simulation software, and you want to, and you solve the mathematical model, and you'll get, say, the displacements and stresses here. Mm-hmm. We get into engineering terminology, and from that, and you can do a buckling simulation, mm-hmm. and then you can say, okay, based on the simulation, this is where the blade is going to buckle, and this is the load at which it's going to buckle. And if that load is too low, what you might have to do is you might have to stiffen the structure mm-hmm. in that particular location where the simulation is telling you that it's, it might buckle. Mm-hmm. That would be an example.
And I'm just kind of thinking about it now, like you mentioned with the wind turbine and it buckling. How powerful are some of these programs?
So that's, again, a good question in terms of when I was in grad school a million years ago, or at least my daughter thinks it was a million years ago. Of course, she's a teenager, and you used to have special workstations, worth tens of thousands of dollars, on which you ran these even simple simulations. Whereas now you can do the basic analysis on, I have a Surface here, on like a regular laptop. But then when you're doing much more complicated problems, that's when you need kind of sophisticated, clusters. For instance, the Formula race car teams use simulations to tweak their designs. And in that case, these are very detailed models, and you really need powerful computers with hundreds of cores maybe to run these simulations. So to learn it and do the basic simulations, you can do it on any computer these days. But if you want to get into more detailed stuff, that's where you need like these really powerful supercomputers.
I know my floor director's ears just perked up when you said race car teams. He's a big race car guy. As I understand it, you've got a few applications of fluid dynamic analysis using ANSYS, as well as finite element analysis. And I want to kind of start at the beginning. What are maybe 4 or 5 examples you're using to help us understand the power of simulation? And as I understand it, you got a couple slides that you want to share with us.
So let me do that. So here is an example. This is a pressure vessel, and these examples have been developed with help from ANSYS, and they are working with lots of different companies. So these are all industry relevant.
Okay.
And so you have a pressure vessel, and it's fixed at the bottom, and there is a nozzle attached to it, and there's actually like a valve system above it that you don't model explicitly, but you can model its effects, and which I show in the certificate program. And you simplify the CAD. The real CAD geometry might be more complicated than what you see here. So that's one of the big pieces of advice I have for students, because often they'll have very complicated CAD models.
Okay.
And for the simulation, you need to just have the major features that might, affect the physics. And then you solve the mathematical model. This is based on elasticity, which I'll talk about more, 3D elasticity, and you can get the stress distribution. This is the von Mises stress. And that tells you, hey, the maximum von Mises stress is going to appearing over here, and which means that the place where that nozzle is attached to the main body of the pressure vessel, that's probably where it's going to fail. You can also, extend this analysis to include the effect of a shock load that might come due to, say, an earthquake. So that gives you an example from a pressure vessel. By the way, that example is from my certificate program. For those of you who might be interested in learning more. So this is the Finite Element Analysis Certificate Program, which is 5 courses, and elasticity applications is based on that particular example. So you see the science, the math and the physics, as well as how you apply it in ANSYS to solve this very practical problem. Another example is the wind turbine blade, which I alluded to earlier. This is a thin wall structure, and it's modeled using shell theory, which I get into in this 4th course, beam and shell applications within that finite element certificate program. And again, here, we simplify the geometry. We have the relative to the detailed CAD. So we have the skin, and we have 2 spars. And then you do the buckling analysis in ANSYS. First, you do a static structural, and then based on that, you can do an eigenvalue buckling. And I get into the underlying science within that that course in the certificate program, and that simulation tells me that, hey, this blade is likely to buckle in this area, and it'll also give me the load at which that buckling is going to happen. And so it'll be like, oh, this is where I might want to make the skin a little bit thicker in order to prevent that buckling, depending on what load you get at which it buckles. And again, the details are within the course. Here's another example. This again came, through our collaboration, the collaboration between Cornell and ANSYS. And this is a turbine disk, say, in turbines, gas turbines. And again, the geometry is simplified. Usually you'll have like holes drilled in here and so on. We ignore that. That's not important for the analysis. And then you have the blades, and it's spinning at, say, 12,000 RPM. So the vibration is very, analysis of the vibration, particularly natural frequencies at which you might get resonance, is very important. And here, a trick is that you can use periodicity to model just one blade. So think about, taking just one blade and modeling it, and then you use periodic boundary conditions. By the way, this is shown in this particular, in the last course within that certificate, vibration applications. And so, and it shows you the mesh, and I'll talk about the mesh in just a little bit. So here again, you're using clever tricks to, simplify the model, which means that it'll run very quickly, and then you can get the vibration modes and the natural frequencies. And if I can go to ANSYS here and show you this animation, even though you're modeling only one blade, you can get these traveling waves, and essentially you have that basic solution, and you, through a phase shift, you can say, oh, you can model this out of plane vibration. So that's another, that's actually from dynamics. That's a very exciting applications. And then there are also, you can basically do any kinds of physics. I work with solid mechanics. My own background is in fluid dynamics. This is a 3D turbulent flow simulation past a car body. It's called the Ahmed car body. I picked this because there's a lot of experimental data against which one can validate one's simulations. So the color shows the pressure on that car body. This is a wind tunnel model. So instead of wheels, you have these supports. And then the arrows show you, where, the direction of the flow. And this is from the other certificate program that you mentioned, Nick. The, excuse me, the fluid dynamics simulations using ANSYS. And this is covered in the 3D turbulent flow. So that's built around that particular application. And the mathematical model is actually very complex, 3D turbulent flows, but one can understand it conceptually, and that's what you need. And in my own teaching, so I use the eCornell material, the videos and so on, and the assessments in my own teaching at Cornell. And then in the Cornell course, of course, students are also able to work on design projects. So the design project they work on is designing the shape of an electric car in order to minimize aerodynamic resistance. So they take what they learned from here and apply it to a very exciting and very relevant kind of design problem. Here is another example, fluid dynamics example, and this is from the compressible flows course within this fluid dynamics certificate program. And this again comes through our collaboration with ANSYS. And here you are simulating high-speed flow over an airplane. And this is a particular model called the DLR F4, for which there's experimental data against which one can validate the simulation results. And so here, it's the airplane, model is stripped down to the fuselage and the wing. And the free stream Mach number is about 0.8. So you actually get over the wing, the flow goes supersonic. So this is a very, very challenging problem where the flow can either be subsonic and supersonic in parts of the flow domain. And again, we go through how do you take the 3D turbulent flow, mathematical model and extend it to compressible flows where you account for density changes. And the whole idea is, you keep building the complexity of the model incrementally. Otherwise, you'll get floored by the complexity of the mathematical model. But that's consistent with how human beings learn. Because new ideas are built on, existing ideas in the brain. It's a very hierarchical organization of ideas. So the way I build these ideas is I build the simpler ideas first, and I explicitly build the more complex ideas on top of that. So that gives you a sense of some, exciting applications. And by the way, what you're trying to predict here is like the forces, right? The drag coefficient, the lift coefficient, and then you can tweak your design. For instance, students, based on the drag coefficient and how much separation you get behind the car, they start tweaking their design.
And you mentioned a little bit about, the teaching and how powerful some of these programs are with some of these examples. How has the teaching evolved over the years with the implementation of some of these programs? Do students need to know the mathematics behind it before doing some of these simulations?
Yes, yeah. So very good question. And I've spent, I've been doing this. I have a fun job teaching engineering simulations at Cornell, as I like to say. And I've been doing this for like 23 years now. And what I've realized, and maybe I'll go to this particular slide, you need to have the software skills, right? You need to know how to generate the CAD, how to put it into a simulation software like ANSYS, or you can do some, often you can do the analysis within the CAD maybe. ANSYS is a very powerful simulation tool, so that's why, and can be used across physics, which is why we use it. So you need to know how to use the software. That's the easier part. But you also need to have a deep conceptual understanding of the underlying science. And this is where what I've realized over the years is you need, as you alluded to, if math is not your thing, that's fine. Because you need to understand the big ideas behind the science. And here I like to invoke Albert Einstein, who you might have heard of. And here's quite a famous quote that says, "I want to know God's thoughts. The rest are details." Within the context of simulation, I would restate this as, we want to know the big ideas. And the rest are details taken care of by the software. This is not how we usually teach, right? Because we teach a lot of the details for very simple problems. And then we also don't teach the connection to what you're doing in the software. So I have made, I distill out the big ideas. And so that's where you're, understanding the science at a conceptual level. But then I also show you the connection to how you draw on those big ideas to, as you're working through the examples. And this is, this I got from the ANSYS CEO, is, what you're doing in the process, you're combining the art of design with the science of simulation. And that's when, you can really unleash the power of simulations to design your product, for instance. And here, to expand on that idea, people, usually call it the black box, right? A sophisticated simulation tool is a black box. So I have this what's inside the black box framework, which might be familiar to some in the audience, because it's also part of my free EDX course. It came out of working with lots of different courses. You were asking me before before the event started about what courses I'm teaching this semester. And I was telling you I work across different courses. I've worked across like 20 different courses because I'm supporting simulation in these courses. And I was going into all these different courses. And to me, it felt like I was giving a different story. This was maybe 10, 15 years back. And I was like, we're using the same tool. There must be a way you can frame the simulation in a uniform way. And so this, black box framework, or what's inside the black box framework, came out of that. And it's been really robust. It's really how every example is framed in the certificate program. And, whenever I go into a Cornell course, for instance, I again frame the simulation this way. So let me go through that framing, because I think this is very powerful, and it gets into what do you need to know about the science in order to use to combine it with the design. So usually, right, ANSYS, say, or any other tool is a black box. You give it user inputs, geometry, mesh, boundary conditions, etc. And you turn the crank and you get color pictures and other results. And of course, the color pictures are a really fun part of simulations. But if you don't know what's, and like I tell students, you might want to show it to your boss and try to get a raise. But if you don't know what's inside the black box, this looks like, as people say in industry, garbage in, garbage out. So how do you move beyond garbage in and garbage out? You need to realize that the software is not solving a physical problem, say the pressure vessel. It's solving a mathematical model of that physical problem, which is built on some physical principles and assumptions. So the most fundamental thing you want to know about the science is, what is a mathematical model? And what physical principles and assumptions are used to build that mathematical model. And then you can input that mathematical model into the tool. It hides a lot of the math. So I make that kind of apparent, like as much of the math as you need to know to make sense of what you do in the software. It'll get you an approximate numerical solution, and that'll give you the primary unknowns at selected points. It won't give you everything everywhere. What it'll give you directly are your primary unknowns at selected points, which you mark out through the mesh. Everything else is post-processing. So when you're in the software, you need to know, I did something. Did I affect post-processing? Did I affect how the mathematical model is being solved? Or did I affect the mathematical model? One of the most common misconceptions I see in students is a confusion between the mathematical model and how it's being solved. These are two separate things. And so, separating those out in your mind is actually very helpful to make sense of what you're doing in the software. You also need to be able to do some hand calculations, and I use this very broadly, like some kind of back of the envelope type calculations, and I show these in the course.
And why is it so difficult for students to make that connection?
Because the math is very complex, and partly that goes to how we teach. Because I think simulation is a disruptive technology in the learning space. Because it's automating a lot of the math, and so you need to know the big ideas, but that's not how we have traditionally taught. So, you have to really fundamentally rethink, how do you teach with this disruptive technology? And my approach is a little bit unusual in that I've embraced simulation completely, because I was like, this is a powerful, you can think of it as a very super fancy calculator. And you need to know, to use that analogy with the calculator, you need to know what is addition, what is multiplication, what is division. But if you want to divide two large numbers, you just use the calculator. And maybe, you can check your result by just saying, approximately I expect it to be, in this range. So I think the reason why it becomes difficult is, I think two things. One is the math can get very complicated, and I see this in, I work across so many different courses. If you get into the details, it gets very complicated, and it's very difficult to, for students to see the forest from the trees. For me, this level of conceptual understanding, it took me 10 to 15 years. And I believe that's partly because of the way I was taught. And so I was like, I don't, it's not necessary to, spend 15 years to understand the big ideas. You can teach in a different way. So that's what the big ideas and conceptual foundations are based on. But the other thing is the connection. Connecting the ideas to what you do in the software. So I see often students, they're like, I need to do like car crashing simulation, and they would go and find YouTube videos, and it's like, oh, I need to click there. It's mostly, if you look at it in detail, it's like you don't know how to verify your results.
Yeah.
So it's often garbage in, garbage out, because you know what to do in the software, but but those videos don't show you what is the connection to the underlying science. So I think there are two aspects. One is understanding the big ideas, but then also connecting it to what you do in the software. And through the certificate programs, that's what we are trying to, show people. And so I think what that'll give you is a very good kind of solid foundation, both in terms of the science and how it's connected to the practice of simulation. And from that, you can build to, lots of complex problems.
And is there one thing that or is there one simulation that students like to practice on or like to do frequently? So like the car crash example, is there one that stands out to you?
I mean, dynamics, car crashes, like in our finite element course where students have to pick problems. We have a combination of mechanical engineering students, aerospace engineering students, and and civil engineering students. Civil engineering students tend to pick bridges. Mechanical engineering students, something to do with cars. They like dynamics. So the car crashing is dynamics, whereas a pressure vessel, is statics. And really in the class we teach only statics, and they're trying to do all these dynamics. So it's like a big jump. In fluids, I would say, simulations of flow past cars is quite popular. Airplanes, but it also depends on what students are working on.
And I actually just got a great question in from Albert, and then we'll kind of get back to it. So Albert asks, what's the best way to convince managers whom know nothing about finite element analysis about the advantages in saving time, money, and accuracy in the design process?
That's a good question. And I have to, confess that I've not had to do that myself because I've done this in academia, basically. But I talk to ANSYS engineers a lot of the time who are doing this in the real world. And for them, the case is very clear. It depends on your particular application, too. And this is where a consultation with the ANSYS marketing team, for instance, or a different marketing team, they can help you make that specific case, like what can you get for your particular application, and here are the advantages. But if you want to make a more generic case, you can probably pick examples, say from like the ones I was showing you, like the wind turbine blade, or depending on what you're doing, or like a car simulation, and show what you can get. And I think this is where like getting very accurate results can be challenging. And so you need to have, I guess, a little bit of familiarity with the simulations to know what you can get out of it and how it would, like help with your product development. For instance, car crashes, right, is one of the, like how do you simulate car crashes is one of the major applications of finite element analysis in industry. So the automotive industry uses, finite element tools such as LS-DYNA to do that. And most of the design and figuring out how cars are going to do in crashes come from the simulations. And you can imagine there is a huge competitive advantage to being able to do it on the computer, crash cars on the computer, and minimizing the number of tests you need to do. In fact, the founder of ANSYS, Dr. John Swanson, who my position was supported through generous gift from him, and he tells a story where he visited, I believe it was Ford, and he was talking to the engineers about their crash simulations, and he said, like, now if the test and the simulations don't match,
Okay.
we check the test first, which is usually the other way, because the other quip is like, nobody believes a simulation except for the person who did it, and everybody believes a test except for the person who did it. So because they have built up so much confidence in their simulations that they are willing to stand by it. Hopefully that was a useful answer.
No, that was perfect, Albert. Thank you so much for your question. And I'll let you get back to it.
Yeah. Okay. So essentially, there's the big takeaway from here is what you're doing in the simulation is you're building a mathematical model and you're solving it approximately using the software. Now, one nice thing about having a framework like this is, and by the way, if you're thinking like this, you're thinking like an expert rather than a novice. Novice is garbage in, garbage out, and you don't need to be an expert and spend 20 years in the trenches. You can start thinking like an expert by knowing the big ideas.
Okay.
The nice thing about having a framework like this is verification validation, which is how you build confidence in your results, comes out of it. So if I go back to the framework, verification, and these have separate meanings, verification and validation, which people use interchangeably all the time, and it drives me nuts, and I kind of tear out my hair, and you can see the results are not pretty. But verification is, did I solve the model right? Whatever mathematical model I picked, do I have a reasonably accurate solution to that? And that depends on your particular application. So for instance, a numerical solution introduces numerical errors.
Okay.
And you want to make sure that those errors are, acceptable. Validation is looking at, whatever mathematical model I picked, is that a reasonable representation of the physical problem? That is, did I solve the right model? That is much harder to answer. And this is where, experimental data comes in. So when you're testing, when you're comparing your simulation results to tests, you're checking that the mathematical model is a reasonable representation of the physical problem. So that's one of the nice things about this framework is that, it points to all the things that you need to do to build confidence in your results. So all the simulations, in the certificate, for instance, and in my teaching, end with verification validation, where you're doing a formal assessment of how good your results are, going back to this framework. Yeah. So, and then, what I was going to talk about is, how do you, what are the conceptual foundations of finite element analysis you need to know in order to use a finite element analysis tool effectively? Shall I get into that?
Yes, please.
So, for instance, right, you want to know conceptual foundations of finite element analysis, and the way, I teach it, I've had students tell me, I've sat with a book on finite element analysis and I was completely floored, right? And whereas, here, this is the kind of introduction I was looking for, where it pointed to the important concepts in a way where I was able to understand it and I can apply it in the software. And in fact, I came up with this. I was floored by all the things in the textbook, right? Because my own background is in fluid dynamics, and after I started this job, I was trying to understand finite element analysis, and I was like, it cannot be this hard. So what I did was I took a simple example, and like the one I have over here, and this is from the certificate, and I worked through it.
Okay.
And all the big conceptual ideas, which I'll allude to in the next few minutes, came out of that. And then once you understand it in the context of the simple example, when you go to something like the pressure vessel, you can just use those ideas because the details get much more complicated, but the ideas are the same. And by the way, this stuff, conceptual foundations of finite element analysis, if you go to the finite element certificate program, it's covered in this course, conceptual foundations, and answers mechanical concepts. So this is the foundations, and the second course is how you connect that to what you do in the tool.
Okay.
So what are some of the big ideas in finite element analysis that comes out of a simple example like this? Say I have I have a bar, and I fix it at one end, and I'm pulling it at the other end with some force.
Okay.
And in general, right, how the displacement, say in the x direction, is going to be a function of x, y, z. It's going to vary at every point in the bar. Now, to simplify the details, you say, you know what? Every point on a plane like this is going to move by the same amount to the right. So I need to find only the displacement at one point. So you're reducing it to a 1D problem. And so you want to find the displacement and the stresses, and the factor of safety, comes from the stresses. So what is a mathematical model? The mathematical model is a boundary value problem. It's governing equations defined in a domain, boundary conditions defined at the edges of the domain. So this is something, that is taught in differential equations course, but for very simple problems. So it's the same idea, but it becomes much more complex. So how do you derive the governing equation for this? You go to Newton's second law. So the F equal to ma, and there's no acceleration, so it's just a balance of forces, which is a free body diagram. So the physical principle is Newton's second law, but what is it applied to? As soon as they tell me, the fundamental law is Newton's second law, I said, what are you applying it to? Because that is also important. What you're applying it to is what's called an infinitesimal element, so vanishingly small chunk of material. That's a trick in calculus. Everything becomes vanishingly small, but they cannot be zero. So you're like at the limit of it becoming vanishingly small, but not zero. That's what the limit idea is. And if you do that, you will get the governing equation, which is the second order differential equation. And this is the body force on it, like gravity. And in fact, you also need to use Hooke's law. But Newton's law is the most fundamental law that you use. And then you have boundary conditions. So you say at the left end, it's fixed. So you'll say, u equal to 0. At the right end, you're applying a force, and you can show that actually sets up the slope. So again, the simple example shows you the two big types of boundary conditions. It's either displacement or the slope of the displacement. And wherever you apply a force on the model, you're specifying the slope of the displacement. And in deriving this, you have to make assumptions. So this is key, and this goes back to the question from the audience is, how do you convince your manager? And that's where basically you can make reasonable assumptions and build a mathematical model. And so these assumptions come out of this simple 1D example. And here also you assume 1D. So when you go to the pressure vessel example, for instance, which is what I do in the certificate program, these assumptions still are valid. The only one we relax is now instead of 1D, it's 3D. Everything can vary in 3D. So you see the governing equations. And so, that gives you a sense of what is a mathematical model. Finite element is not a way to build a mathematical model. It's a way to solve the mathematical model. So, let me talk about, how do you solve that numerically using the finite element method, and what are the primary unknowns at selected points? So I'm moving from talking about the mathematical model to talking about how do you solve it using the finite element method. So two big ideas, discretization and interpolation, that come on this one slide. So you say, you know what? It's very hard to find the displacement everywhere. So what I'll do is I'll find it at selected points. So here, as a simple example, I will find it at 4 points. And these are called the nodes. So you reduce the problem to determining U values at selected points.
Okay.
And so what if you want to know, say, the value here? You just use an interpolation between those two values, and that looks like that. So that's just, you have a linear variation between the nodes. Now, if you're doing a finite element course, at this point, you would do a deep dive into what are called shape functions, which some in the audience might have seen. What I've realized is when I'm in ANSYS, I never have to think about shape functions because all that is automated. But what I have to think about, what I need to know, there is an interpolation, and I need to know the order of the interpolation.
Okay.
So I never get into shape functions, in this particular certificate because that's a feature that's automated.
Yeah.
So this is a big idea, the discretization. So you've gone from determining U everywhere to determining it at 4 values. And in a real model, it'll be thousands or even millions of points. But the same idea. And you would say, the degrees of freedom in my finite element model is 4.
Okay.
So how do I find those 4 values? So the big idea is that you take your differential equations with boundary conditions, your boundary value problems, and you derive algebraic equations, a system of algebraic equations. So you'll derive 4 algebraic equations. And for that, you have to use the polynomial interpolation that I was talking about, the element by element polynomial interpolation for U. This is a very complicated step if you, the way it's usually presented. But again, when you do it in the context of a simple example, like I do in the certificate, it becomes tractable. You see, you go to this integral form called the weak form, and then you substitute your element by element polynomial interpolation, and out will pop the algebraic equations. Wow. But the nice thing about that is you see what are the errors introduced in the process, because in this step there are errors introduced, and you see how you minimize those errors. So that's my interpolation. And then solvers these days, computers these days, you throw like a million algebraic equations, they'll solve it for you. And you will get those 4 values, and then everything else is post-processing. Because through the interpolation, you can get the displacement everywhere and so on. So that gives you the big ideas. And then, from this, for instance, in the when you do the solution, in the certificate, we actually go through and do the, go through the deriving the algebraic equations and solving them. And you see that, you get these 4 values, and you can compare it to the exact solution. For the simple problem, you have that. And you see it matches very well.
Wow.
So the solid line is the finite element solution. Now, when you want the stresses, so this is the stress, you have to take the derivative. And here, the stress varies linearly, so that's this line here, whereas my finite element solution says that the stress is constant. And so you see there is this error in the solution, and a big idea that, 2 big ideas that jump out of the simple example that applies to more complicated problems. One is that the stress is discontinuous across elements because the slope is discontinuous, but the error in stress is much greater than the error in displacement. In ANSYS, for instance, I see students, the only thing they will look at in the results is the stress. And I'll say, that's, first of all, you don't have an intuitive feeling for what the stress is. Plus, it has a lot more error than the displacement. So look at the displacement. You have applied the pressure on the pressure vessel. How is it going to, is it expanding? So do some sanity checks. But so through the simple example, you get to the big ideas, and then, it also gets like, how do you reduce numerical error, which I will skip in the interest of time. But the important thing is you draw upon this when you get into the pressure vessel. So all these you can, to understand the science behind the pressure vessel simulation, now you go back to these ideas. And, I can, maybe at this point, I can briefly allude to that. For instance,
Yes, please.
the governing equations, right? So this is where, when you get into the 2D, so this is the 1D case. This is the one I showed you. And there's a whole chain of reasoning used to derive it.
Okay.
The corresponding equations in the 3D are this.
Okay.
So when you see something like this, it's kind of overwhelming if math is not your thing, which for a lot of people it is not their thing. But you can still be a great engineer because we have these tools. In fact, when I talk to people in the industry, most of them have forgotten all their math.
Oh, wow.
But they're using CAD and simulation tools all the time because the math is automated by these tools. And so essentially the strategy is you use the 1D, you understand the math in 3D, much more complicated by analogy to the 1D. So again, it goes back to the idea of new concepts and new ideas in your brain is built on old ideas. So if you have a strong understanding of the 1D, you can understand the 3D by anchoring this much more complicated 3D idea in the 1D. This is not how we usually teach. And so by using these analogies and not getting into the details, because the details are taken care of by the software, you can really get a good conceptual understanding of the governing equation of 3D elasticity. I won't get into the details here. So so you understand the mathematical model by analogy to 1D. And again, you see, the assumptions are the same as in 1D that I alluded to. Very important for the engineer to know. What are the assumptions built into the mathematical model? Because your results are only as good as your mathematical model. But the strategy used by ANSYS to solve it is the same as for 1D. So that's why I go back to this particular slide, say, hey, the details get much more complex, but the overall strategy is the same. And that's what you need to know as the user. The other thing you need to be able to do is, make some hand calculations, right?
Okay. Oh,
this is where I tell students, talk to experienced engineers. They will tell you what kind of expected results they get. So for instance, I'll show you an example for the pressure vessel. And this actually, an ANSYS engineer showed me. It's a very cool trick. First of all, there are multiple things you can say about the results. For instance, here the geometry is symmetric. We've simplified the geometry to be symmetric about an axis. If you cut it like over here, it's symmetric. This half and that half would be symmetric.
Okay.
So we expect the displacement and stress contours to be symmetric. But the reaction, so I'm holding it here, and I can actually predict what that reaction should be based on a simple kind of hand calculation. And here, the idea is that, say, if I have a closed box with just an opening, and that corresponds to this opening here. So this force over here is not balanced by the force over here. Whereas, in this region, where I've not highlighted it, this force due to this pressure is balanced by that. Yeah. So the imbalance is going to be just the pressure times this area. And you can do that for that area. And you can say, hey, it has to be 500, and then that imbalance load due to this opening is 512 pound force. And you also have the weight. And the total reaction should be a combination of that. So you can check that. So, in ANSYS, when you implement it, you have to, you input the Young's modulus. And to make sense of that, you go back to the governing equation and say, this is something that appears in D, the material properties. So the big thing is that you're connecting what you're doing in ANSYS to the underlying science. And then you look at the results. This is symmetric. And verification, it's like you apply the load in 2 steps in answers, and you see, boom, it matches. And answers is, deriving the algebraic equation. It's doing a much more complicated thing. But this is a sanity check. So there are more examples like this within the certificate. And so, for instance, if I go to that particular course, Elasticity, this is where so there are 2 sections, right? One is review the big ideas. So we go through and derive the governing equation, which I showed you by analogy to the 1D. And each of these, this is active learning because you have the video and then you have a quiz. So if I say resume quiz, so you're learning something in the video, it's what? 8 minutes long. That's typically the length of the video. You saturated your short-term memory in that time. So you have the question to apply that knowledge. And you can see it's a non-trivial question. So you have to really understand what's in the video you often have to go back. Students tell me they have to go back to the video to answer the question. I was like, mission accomplished. But then you go to, so when you're in answers, right? So I show you how you input the mathematical model into answers. So if I go to that particular step, so this shows you how to do it in answers. And here, you're looking at the video, say, that's me on camera first, and then you're looking at the governing equations, and then you're in answers. So you're specifying the governing equation, specifying boundary conditions. So that gives the audience a sense of how the learning within the online platform is active. You're learning something, you're answering quiz questions. You are seeing something being done in answers, you're following along in answers. And there are 2 ways you can get access to answers. One is you can go to answers.com/student. And download the free Answers Student product. All these examples can be done using the free product. And the other is if you go to course shortcuts. So some people in industry, they are not at work computers. We've talked to companies adopting the certificate. They cannot download software. So if they don't have answers on their computers, they cannot download it to their work computers. For that, you can use this Answers Online option that we have. So you can run Answers in the web browser. So those are the 2 options within the, one within the course and the one through the Answers, free Answers download that you actually can, implement these things in Answers. So it's a very hands-on learning, which is, right, it's hands-on. It's very visual. I think simulation is fun.
No, it is. It is very fun. And I want to kind of take a quick step back. Robert checks in with something you mentioned earlier. So Robert says he's studying in MSc in aerospace engineering at Manchester University. For my dissertation, I'm numerically analyzing the car's aero stability performance via CFD. What could be good, cost-effective physical methods for validating these studies?
So
again, the car crash.
So again, right? So this is where, I'm a jack of all trades, master of none at this point because I've worked across 20 courses. I know the foundations. And so, thanks for the question, Robert. So there are 2 things, right? There's verification and validation. So verification, it's like you want to check that, first of all, you need to know what your boundary conditions are. So you need to know is are the behavior at the boundaries, does that match your boundary conditions? That's a basic check. You can look at the mass imbalance, say within ANSYS, which I show in my, I show the basic checks that you can do.
Of course.
That's the first level of checks you want to do. You want to do the sanity checks. Then you want to check the numerical error, like, boundary conditions. You want to check the numerical error. And that's a verification. So you say, I have a pretty good idea that I'm confident that I've solved the mathematical model correctly. For validation, you need to have experimental data.
Okay.
So I would say try to find similar problems in the literature, maybe much more simplified. I find students being hesitant to solve like much simplified problems, but those are actually great places to, like build your confidence. So I alluded to the Ahmed car body. Like that's, before students do the real car, they do the Ahmed car body, because there you can go into the literature and there are results that you can, you can compare your simulations against. So those are some strategies that you would use to build confidence, and that Robert could use to build confidence in the results. And then ask your advisor, ask senior engineers, use online discussion boards.
Very much so.
Yeah.
And Robert, thank you so much for that question. I hope we answered that for you. So we got just a little bit of time left. Rajesh, thank you so much for coming in and explaining everything. And audience, we hope it was helpful. So if you could kind of reach out to our audience, Robert, all the people that ask questions, and kind of give them one thing to think about or one thing to walk away with when they're thinking about developing these simulations and testing some of their problems and everything. What's that one thing you would want them to walk away with or kind of think about?
Don't be intimidated if math is not your thing.
Okay.
Right? And that's where, we need to change the way we teach. That's very hard to do, but I'm an evangelizer in that. And I've had a lot of people sign up for my free course on EDX, and this is taking it to the next level. You can really you need to understand the big ideas, see if you can and this is where again you want to talk to colleagues, you want to talk to your advisor, make sure you understand the big ideas behind the mathematical model and the numerical solution strategy. Often these can be understood in the context of very simple examples, and then draw on those ideas when you are, in the software. Use the YouTube videos. They are great to figure out what to do in the software, but do take the time to, to really understand the underlying big ideas, about the science on which the simulations are built.
Perfect. Well,
yeah.
Rajesh, thank you so much for joining us. Audience, thank you so much for all your questions. We really appreciate it. Have a good afternoon, and we'll see you at the next keynote.
Thank you so much. Happy simulating.